Okay, so thanks very much. Everyone can hear me okay? Okay, good. Right, so first I should also start by thanking the organisers very much for putting together this wonderful meeting. It's very nice to be here. Indeed, what I would like to talk about this morning is some work on probabilistic ways, probabilistic algorithms, I guess you could say, which we can use to simulate quantum experiments within this framework of so-called quantum computational supremacy, or even just quantum supremacy. So what does this mean? Well, it's a maybe slightly terrible phrase, but it's not totally clear that there's a better one that we have yet. But what it roughly means is some computational tasks which we can solve efficiently on a quantum computer, by which I mean maybe in a few hours or days, something like this, but which any classical computer would take an extremely long time to solve. So there's no, I guess, rigorous definition of this, but we could say, well, maybe a supercomputer would take over a year to solve the problem. So we think that within a matter of years, or maybe even a matter of months, we will indeed perhaps see some experiments that are demonstrating this kind of separation. So it's kind of an interesting thing from a theoretical point of view to study how such separations can be achieved. And in particular, if we want to show that we have something that a quantum computer is doing that no classical computer can do, we really should try quite hard to find algorithms that we can run on a classical computer that are trying to solve this task more efficiently than maybe a naive algorithm does. Because if we want to have a convincing demonstration of the power of quantum computers, we ought to really try as hard as we can to make the classical computer succeed in solving this task. And what I want to talk about today is some algorithms which kind of try and address this challenge and try and solve some of these problems that people have proposed to use to demonstrate quantum supremacy more efficiently than we might have thought that we could. Okay. So in some sense, this, well, maybe somewhat pushes back, the goal of quantum computational supremacy slightly further into the future, but well, I don't know, we can discuss this. So what I want to talk about today is work in a couple of different papers. This is joint work with a number of people. So I want to talk about two computational models, one called IQP, which is short for instantaneous quantum polynomial time. And this is joint work with Michael Bremner and Dan Shepard in this paper here. I want to talk about some work on a problem called Boson Sampling, which many of you may have heard of, which is joint work with quite a number of people, Alex Neville, Chris Sparrow, Raphael Clifford, Eric Johnston, Patrick Birchall, and Anthony Lang, all from Bristol. You can tell from the number of authors that this is an experimental group that I've worked with. And this is a paper in Nature Physics, which is also on the archive. And there's also a survey paper on some of these topics, which is joint work with Aram Harrow, who is here, which you can also find now from 2017 if you're interested in learning more about this general area. Okay, so in general, in quantum computational supremacy type proposals, what we're looking for is some kind of architecture for a quantum experiment which is quite easy to implement, because we want to demonstrate the superiority of quantum over classical as easily as possible. But we also want to find some kind of good evidence that this quantum experiment, this quantum architecture that we've proposed, should be hard to simulate classically. And people have found a number of different proposals for achieving this, specific classes of quantum computations which we think we can implement fairly easily, but which we think are hard to simulate classically. It's kind of notable that these end up being based around some nice mathematical problems, which is good because we can use the mathematics of these problems to come up with some evidence for hardness. But on the other hand, this might make it easier to attack these problems classically. So maybe it's like the Achilles heel of these proposals. And I guess it's also worth stressing at this point that these proposals for demonstrating this superiority of quantum over classical, they are not intended to really solve anything useful at this point. So we're not trying to find problems which we really care about that we can solve if we don't care about demonstrating quantum can outperform classical. We just want to come up with some convincing demonstration that quantum is better. We don't want to solve a useful problem just yet. But okay, so there's two of these architectures I want to talk about today, and the first one I want to introduce is this model IQP. And sort of operationally, we can think of this model as looking like this. We have a quantum circuit of n qubits, and it's a circuit of a very specific form. I'm just going to draw. Okay, apologies, my inability to draw straight lines. So this is a quantum circuit on n qubits, where we start out with every qubit in the 0 state. Then we apply a Hadamard gate to every qubit. Then we have some other circuit here in the middle, where all of the gates in D are diagonal in the computational basis. So they all commute, they're all diagonal in the same basis. And then we have Hadamard gates again, one on each qubit. And then we measure each qubit in the computational basis, and this gives us an n-bit string, a string of zeros and ones, and we output this string, and this is kind of the output of the computation. So this will sample from some distribution that depends on what the gates are in this D here. And the title instantaneous quantum polynomial time, IQP, refers to the fact that because all of the gates in this circuit here commute, in some sense they could be applied at the same time. There's no time ordering between them. So even though physically we may have to apply them one after the other for kind of experimental constraints, in principle we could do them somehow all at once. Okay.
They commute on the same line of whatever qubit you use.
Right, that's correct, yes. So they're all diagonal in the computational basis. So they all, even the ones that affect the same qubits, they commute with each other, correct. So it's not just that they're acting on different qubits. Okay. Now, mathematically, what does this correspond to? Well, if we define a function f of x, which is just the xth diagonal entry of this matrix D that we get from combining all of these gates here, then we get some distribution on bit strings S, which looks like this. Okay, so if we define some function which tells us the diagonal entries of this matrix D, then the probability that we see a particular outcome S, and one n-bit string at the end, is just the absolute value squared of a certain Fourier coefficient of the function f. So this is the Fourier transform over z2 to the n. We take the Fourier coefficient, S-if Fourier coefficient, and we take the absolute value squared of this. So this, so what do I mean by the Fourier transform of f over z2 to the n? Well, more concretely, it looks like this. We just have this sum over different values of x with some normalization of f of x times by this character of the group z2 to the n. Okay, so this is very nice because this means that we can understand the properties of this probability distribution in terms of some simple Fourier analysis. Okay. And these circuits have some very nice properties. In particular, so I should say they were they're introduced by Shepard and Bremner in 2008. In 2010, Bremner, Joseph, and Shepard showed that they are hard to exactly simulate classically if you assume some computational complexity assumptions, some widely believed computational complexity assumptions. And then in 2015, Mick Bremner, Dan Shepard, and I showed that they're even hard to approximately simulate. What does this mean? I mean, if we set the task of sampling from some distribution which approximates this distribution on outcomes S up to small total variation distance, let's say 0.1% total variation distance, then the task of achieving this classically should be computationally hard if you make some additional computational complexity assumptions. Okay, so I don't want to go into these today, but in general, in computational complexity theory, you never really prove anything, you just prove it subject to assumptions, and these are definitely examples of this general theme, that we don't have cast iron rigorous hardness proofs, we have proofs subject to assumptions. Okay, but still, this sort of class of circuits is relatively easy to implement experimentally, and there's some evidence that they should be hard to simulate, so this makes them kind of tempting targets to try and demonstrate quantum computational supremacy. Okay, so that's the first model I want to introduce, and the second one I want to introduce is called Boson Sampling, and this model looks like this. Okay, so this is the I guess, computational problem that corresponds to simulating the behavior of non-interacting photons in a linear optical network. So basically, the easiest way to think of this is in terms of a particular experiment where we start out with n photons here, n single photons, and we have a linear optical network that has m modes, so lines that the photons propagate along, let's say. And then within this network, we have some components like beam splitters, phase shifters, things like this. And then at the end, the photons come out of this network, and we have a detector at each of these lines that either clicks or doesn't click, or perhaps it even tells us how many photons have turned up at each particular point. And we end up, we had n photons going in, we have n photons coming out, but the question is where they come out. So sometimes they may be in one particular set of modes, sometimes they may be in some other set of modes, and so we have some kind of distribution on subsets of modes where they can appear at the end. So this also has a nice mathematical description. So we can say that the output distribution is a distribution on subsets of the integers between 1 and m, which tell us where we're associating each of these kind of lines with an integer. And we get a distribution on subsets of size n of this, corresponding to the different places that the photons can appear. Now, we might think that sometimes we have two photons appearing in one place, or something like this. So two photons coming out of the same line. But if we assume that m is very much bigger than n, so it could be bigger than n squared, for example, then this doesn't happen in general. So we're going to be making this assumption throughout, which just simplifies things. Then the probability that we get some subset S of the outputs modes, which are the ones that the photons appear in, is equal to the permanent of a certain matrix. What's the permanent? The permanent is, for those of you who haven't seen it, it's like the determinant, but you don't have any signs. So it's a sum over permutations of the integers between 1 and n of a product of matrix entries given by that permutation. And what's this matrix A here? So the whole linear optical network is described by some unitary U, which is an m by m unitary matrix, and then A is the matrix corresponding to the first n columns of this. So mathematically, to define this problem, we start out with an m by m unitary matrix U, then we look at the first n columns of that, and then our task is to try and sample from this probability distribution here. It may not be obvious this is indeed a probability distribution, and in fact it's not, but when m is much bigger than n, for most matrices U, it's close to being a probability distribution, so we can, for the purposes of this talk, just assume that it is. And the task is to sample from this distribution here. So, okay, so some first observations are that this is a distribution on many, many things if we think of n being large and m being much bigger than n. So this is a distribution on obviously m choose n on m choose n, which is bigger than m over n to the n elements. So this is exponentially big in n. Like if we could, for example, think of m being n squared, then this is bigger than n to the n. So this is a very large space to try and sample over. And this problem was introduced by Scott Aronson and Alex Arkhipov back in 2010, who gave evidence that this is hard to approximately simulate up. So by which I mean, if we want to simulate to the IQP setting, if we want to sample from this output distribution up to small total variation distance, like maybe 0.1% or something, then it's hard to do this if you assume various conjectures. There was a computational complexity one and also a mathematical one. But these are kind of plausible conjectures, and if you assume them, then you get some computational hardness result here. But an interesting question here is, how hard is this problem really in practice? Because these things, these linear optical networks are designed to be easier to build than full quantum computers, but they're still not that easy to build. And we would like to know exactly how big a network we need to build in order to achieve this, and how many photons we need to use, because getting n photons to appear all at the same time is a very difficult thing to do. And so people have had various estimates on, in practice, how hard this problem should be to solve. And these estimates have kind of evolved over time. Some people, for example, this first paper by Aronson Arkhipov, also John Preskill and some other people, have suggested between 20 and 30 photons, so that's n is somewhere between 20 and 30, should be enough to demonstrate quantum computational supremacy. So again, by which I mean something which a supercomputer couldn't compete with. But this number has actually gone down over time, and there's even been a suggestion that with n equals 7, you should be able to demonstrate quantum computational supremacy. So this would obviously involve making m very big here in order to get something which is quite a big distribution to sample from. So, I guess it's fair to say, we still, didn't really know, like, how complicated this problem was going to be in practice. I mean, certainly, if you just want to write down this distribution, then it gets very hard very quickly. Okay. Let's see. Okay, so what I want to do now is talk about our results. So we have a result about IQP where roughly speaking, we consider how hard IQP is to solve with realistic level of noise. And in the case of boson sampling, we have a result about how hard boson sampling is to solve kind of in practice. I just realized I actually want to edit this circuit here for about IQP, so I'm going to bring it back down again. But this also gives you a chance to see it, from different perspectives. Okay, great. Right, so what I want to think about now is a model of IQP circuits with a kind of realistic, somewhat more realistic notion of noise than just saying we're looking at output distributions that are close to the, arbitrary output distributions that are close to the real distribution. And this is a very, very simple notion of noise, where we look at the end of the circuit and we add some noise here just before the measurement. Okay, and what's the noise that we're adding? It's depolarizing noise with rate, epsilon. So we map quantum states like this. Okay, so this is just the qubit depolarizing channel. So it maps a quantum state to itself with probability 1 minus epsilon, and with probability epsilon it randomizes it, throws it away and replaces it with the maximally mixed state on one qubit. So we're assuming that just before we measure we have this kind of this relatively simple type of noise happening. And in fact this noise commutes with the measurement operation, so we could also have put this after the measurement, and then what this corresponds to is that we do the measurement, and then with some probability, let's say epsilon over 2, we flip the measurement outcome of that particular bit. So you can also think of this as kind of classical noise in the measurement results. Okay. So we want to understand how hard it is to simulate IQP circuits if we have this rather benign-looking notion of noise coming in. Okay. Right. Now I can get rid of it. Okay, so if we call the distribution on outcomes P, probability distribution on different measurement outcomes we can receive, now we're going to have to make an assumption that the L2 norm of this thing is small. So the sum of the squares of the probabilities is at most alpha times by 2 to the minus n for some alpha that's going to be a parameter in the result. Okay. Then what our result is that we can simulate this circuit classically, the problem of running the circuit and then sampling from this distribution up to L1 distance delta and time n to the order log alpha over delta divided by epsilon. Okay. Now, okay, so let's just to unpack this expression here. Remember, so epsilon was the noise rate that we had up here. Alpha is just this parameter, which is just some value for some particular distribution p, and then delta is the accuracy with which we want to simulate this thing classically. And what this result says is that if all of these things are constants, say order 1, then we can simulate this thing classically in polynomial time. But as I'm sure you've already noticed, the exponent in the polynomial is horrific. So if epsilon is 0.01, then this is going to be at least as bad as n to the 100 or something like this. So this is not necessarily practically efficient, but what it does say is that you have not got an exponential quantum speedup for the problem of simulating this noisy IQP circuit. Okay, so we can simulate this noisy thing in polynomial time. And this is a very kind of simple notion of noise. So this suggests that if you have more complicated noise, then this does not bode very well for the classical hardness of this either. Okay. And just to comment on this parameter alpha, why is this important? Well, the hardness proofs that we have for simulation of IQP circuits needed to assume that alpha was order 1. This is a so-called anti-concentration assumption. So if alpha is not order 1, then actually we don't have proof that the circuit should be hard to simulate in the first place. So the circuits where alpha is small are actually the ones which are kind of interesting from the perspective of computational hardness. And in fact, you can show that almost all IQP circuits have alpha is equal to order 1. So if you pick the circuit at random, then in fact, the probabilities are going to be very spread out, and something like this will hold. Okay.
Your X is the S from above.
I'm sorry? Oh, yes, yeah, sure. Yes, sure, okay, so it's...
Probability test, right?
Yes, absolutely, yes, so, sorry, yeah. I'll just make this S, then maybe it makes it a little bit clearer, yes. Yeah, thanks. So, right, so in fact, for almost all circuits, this gives a relatively good simulation, if an expression like this seems good. Okay, but it's also worth saying that we can evade this result with classical error correction. So it turns out that we can encode the IQP circuit in the D there above with some kind of classical error correcting code which enables us to still get hardness. So if we encode it with some notion of error correction, then effectively the circuit doesn't get affected by this noise anymore. And this theorem ends up not applying. So the interesting thing about that is that the notion of error correction that we use is much simpler than full quantum fault tolerance. You just need to use effectively just a classical error correcting code. And in fact, the error correction works for any noise rate. So we don't, we somehow get a complete, converse, I guess, of this result. That this result says for any epsilon that's strictly bigger than 0, and with alpha and delta fixed, you get an efficient simulation. Whereas the error correction result says that for any epsilon that's less than 1, we can still get hardness of classical simulation if we encode the circuit appropriately. Okay. Right, so that's the IQP result. And then the Boson sampling result, which I guess I'm only going to mention briefly, is that we can use a simple classical algorithm called metropolized independent sampling, which is a very simple example of a Markov chain Monte Carlo algorithm. And to sample from the Boson sampling distribution, with good accuracy, by computing order 1 n by n matrix permanence. Okay, so this now is not a mathematical result, this is an empirical result. So we tried using this algorithm numerically, and we did some experiments with it, and it turned out that it was pretty good. We have some statistical evidence that it's doing a good job of sampling from this distribution. But we don't have a proof that this algorithm does work well. But just to highlight what this means, what does it mean to say, well, we can sample from this distribution by computing order 1 matrix permanence? We can compute an n by n matrix permanence in time order n times 2 to the n by an algorithm called Reiser's algorithm. And what this means is that we can get good accuracy for larger sizes of boson sampling experiments than people thought previously would be accessible. Okay, so what levels of accuracy can we achieve? Or so what sizes can we get to, I should say? We can do n equals 20, so 20 photons on a laptop. We can do n equals 30 on a fast server, or something like this, maybe a few of them in parallel. And we can probably do n equals 50 on a supercomputer. So we didn't do this, but this is based on the best known bounds and projections on computing matrix permanence.
Didn't someone compute a big permanent on a supercomputer?
Yeah, so there's a paper about this. It's great because the title is like computing n equals 50 permanence on a supercomputer, but they never actually did n equals 50, I think. They did like a few less, n equals a bit less than this. Some other quibbles one might have is to do with numerical stability and things like this. But simply in terms of like the raw runtime, like you expect to get up to about n equals 50 on a supercomputer. You might have to be careful with, that your numbers, are really accurate enough and things like this. But just in terms of the complexity of the algorithm, this is probably about right. Okay, and then also I should say later on in 2017. It's a paper by Peter and Raphael Clifford, which gave a provably correct exact algorithm for boson sampling. And their algorithm runs in time like order, I think, n times 2 to the n 2. So, comparable time to this one here. The result here is just an empirical one. Like the algorithm seems to work well, and their result is a provably correct one. So what this shows, I guess, is that demonstrating quantum computational supremacy using boson sampling is going to be harder than we thought before. In the paper, we have a beautiful picture which I didn't draw, showing the various parameters that people have achieved so far and how far you would have to go in order to get a very substantial separation between quantum and classical. And things are looking very challenging. I mean, you would probably need to have over 50 photons, for sure, 50 or 60 photons, and you need to have each of them surviving all the way through to the end of the circuit with probability at least a half or something like this, which is an experimental challenge, though, definitely not ruled out, but it's going to be challenging. Okay. Right, so just the last few minutes, I just want to say a few words about the proof techniques for this one, and also a little bit about how this algorithm works if I have time, so I'll just spend a few minutes on each one. Okay, so the IQP proof sketch first. So a nice thing about IQP is, as you can see from the description up there, it has this nice description in terms of Fourier analysis. And we're also going to use this in the analysis of the noise that we have here happening in the circuit. So what one can show is that if we have some noise occurring in an IQP circuit like this, then this has a nice effect on the Fourier coefficients of the probability distribution at the end. So if we have, if we call the probability distribution P, then we can think about the noisy probability distribution P tilde, which is the one that we get after we've had this local noise occurring. And we can define the Fourier transform now of this noisy thing. And it turns out that the Fourier coefficients, I'm now using S far too many times, but apologies for that. The Fourier coefficients of this thing S are exponentially suppressed for S's that have large Hamming weights. Yeah, okay, so here, this symbol just means S is an n-bit string, and this is the Hamming weight of S. So what this says is that many of the Fourier coefficients are going to be suppressed very substantially for epsilon being a small constant. And what this means is that if we know just a few of the low-order Fourier coefficients of P, then this is enough to enable us to reproduce almost all of the kind of noisy version of P here. So we only need to compute the low-order terms in the Fourier expansion of P in order to have a very good approximation to the noisy version of P. Okay, and this is an observation which holds for all quantum circuits. We haven't used the fact it's IQP yet, but the way in which the definition of IQP comes in is that we can approximately compute these coefficients using Fourier duality, which enables us to show that the following expression holds, right. Okay, so if P is this output probability distribution again, then the Fourier coefficient P hat S, you can just work out using Fourier duality that it's given by this thing here. So this is basically the convolution of F with its complex conjugate. And this thing here on the left-hand side, we can approximate efficiently just by doing some simple sampling. So if we pick a random y and compute this product here and take the average over some number of y's, this lets us approximately compute this thing here. And if we do this for all of the low-order ones, the ones where this Hamming weight of S is small, then this is enough to approximately understand the noisy version of P. And you can calculate you can calculate the bounds on how many of these coefficients you need to know, and it turns out that it's enough to know this for all S, such that size of S is equal to order like log alpha over delta divided by epsilon. Okay. Right. Okay, so that's the rough sketch. There are some technical details as well, but I'll just leave it there for today. And finally, I guess I'll mention the boson sampling algorithm. Okay, I'll stop there. Okay, so the boson sampling algorithm is based around the idea that we can efficiently sample from some related-looking distribution which is the so-called distribution on distinguishable photons. So these are photons where we imagine that each photon has a little label attached to it so we can track it through the circuit. And this distribution somehow looks very similar to the one which is right up there in the top corner. The only difference is that the absolute value squared is in a different position. It's on the inside of this permanent rather than on the outside. And it turns out that this means that you can efficiently sample from this distribution. There's again, a distribution on subsets of the outputs, but you can efficiently sample from this now. And effectively, this is because you can treat each photon separately, and you can just you have a kind of fully classical problem. It's a bit like throwing balls into bins or something like this. Okay. So this is the one that we want to. This is the one we can sample from. The one that we want to sample from is the one that I wrote up there in the top corner, but I'll just write it again here. Okay, and to do this, we have this process where which again I should stress, this is a really well-known, very simple algorithm, where if we assume that we have a bunch of samples that we're producing, and some samples x, and we want to get a new sample x prime, then to get this, we we want to get some new sample, let's just say. So we take a sample x prime from this distinguishable distribution D, then we accept this sample with probability, which is just given by this. Okay, so you accept this new sample with probability given by this thing, which is a minimum of 1 and this product of these ratios. And you can show that the stationary distribution of this process is just the same as this distribution, pi, which is the one that you want to sample from. And how can you compute these things? Well, in order to, you already know these ones for x, and to compute these ones for x prime, you just need to calculate some matrix permanence, which you can do in time, like 2 to the n times 2 to the n. So you repeat this process. You do need to throw away some of the samples, because if you just take samples one after the other, there'll be some kind of correlation between them and things like this. So empirically, it seems that you can get away with throwing away about 100 samples per actual sample you end up producing. But still, the evidence is that if you do this, that you get some very good convergence to the real distribution. And like I say, it's a very simple algorithm. It goes back to at least the 50s, I guess. So it'd be interesting to see if we can do anything, better with some kind of more advanced algorithms here. So just to summarize what I've said, now it's the end of the talk. In each of these cases where we have a proposed architecture for quantum computational supremacy, it turns out you can do something non-trivial by thinking a bit harder about what the classical algorithm is that's supposed to compete with the quantum algorithm. And in the case of IQP, we have this algorithm for simulating noisy circuits, but you can evade this algorithm using some simple classical fault tolerance. And in the case of boson sampling, we have these algorithms which are more efficient for small systems than you probably, than we previously thought. Of course, they still become ineffective for large systems, but if we have some very large experiment, this is also hard to implement quantumly. So perhaps we need to design some notion of fault tolerance for boson sampling as well that enables us to go to these larger systems if we want to use this approach. Okay, so that's everything I wanted to say, so thank you very much.